The number of stereoisomers of the molecule depends on the number of chiral centers that you have. For example, this molecule here has two chiral centers. Again, you guys, every single molecule we represent it as a skeletal form. So definitely there is a hydrogen here and there's a hydrogen in there. And these are your four different groups. For this chiral center, you have, let's highlight the groups. You have a group here, a group here, you have a group here, and you have all of this for this chiral center. We do the same thing for the other chiral center in there. So these two are chiral centers. So the number of stereoisomers is 2 to the n. So that is going to be 4 stereoisomers. This is the maximum number of stereoisomers that you get out of this formula in here. So this formula is used to calculate the maximum number of stereoisomers that you can get out of your molecule. In order to represent those stereoisomers, we use the Fisher projection method. So Fisher projection is a method that you use in order to draw structures that have more than one chiral center. You can draw Fisher projections using one chiral center, two chiral center, up to X chiral centers in there. A Fisher projection is represented by a vertical line and a horizontal line. When they meet at a carbon. This carbon can be chiral or it cannot be chiral. It depends on the molecule itself. They cannot be chiral. Normally, the carbon chain, we draw it on the vertical line. And on the horizontal line here, we have our hydrogen. The vertical line means that it's kind of like similar to eclipse. Any compound or any molecule that is on the vertical line, this means that it is behind. And any molecule that is on the horizontal line, it means that it is in front. So a Fisher projection like this is the same as this structure here. And as I said, Fisher projection can be up to X number of carbons in there. And it depends if these carbons are chiral or not. They should be surrounded by 4 different groups. So let's show how many stereoisomers we have for this molecule using the Fisher projection of this molecule. The first thing you need to locate is your chiral centers in there. We have a hydrogen. Notice that I did not consider the stereochemistry of the hydrogens, whether they are in front or behind. It honestly doesn't matter in here since I'm going to draw all the stereoisomers possible. So the number of stereoisomers is 2 to the n, where n is the number of chiral centers. I have 2 chiral centers in there, so this is a total of 4 stereoisomers. Reactions, I do have 2 chiral centers. I have a chiral center here and I have a chiral center in there. And in between there is a CH2. So I'm going to start drawing my Fisher projection. Here you go. In there. So this is going to be my CH2. This is a hydrogen and this is a hydrogen. Now I'm going to start with my first chiral center, which is, I'm going to label it as carbon number 3 in there. So you have carbon number 1, which is a CH2, CH3. Carbon number 1 is the CH3. You have carbon number 2, which is a CH2. And then you have the chiral center, which is carbon number 3 in there. You have carbon number 4. And then this is the CH2, and then you have carbon number 5, which has the OH and the hydrogen, and then on carbon number 5 I have 6 and 7. So I have the CH2 and I have the CH3. Now let's go ahead and put the groups around carbons 3 and carbons 5. For carbon number 3, I do have 2 groups around it. Other than the long carbon chain. Now the long carbon chain is already included. We did before. There's a rule for Fisher projection, and I don't want you to confuse this with the R and the S rule that we did before. So before, remember, we said like we are inverting the group so that the lowest priority group is always going to be behind. This is what we said whenever you are figuring the R and the S configuration in a 3D molecule. So if you're working with a 3D molecule, always make sure that your hydrogen is behind. But with the Fisher projection, we're always going to go with the hydrogen group being in front. And then every single time we need to invert the configuration. You don't have any other option. So we said that whenever we are working with a Fisher projection, that the groups that lie on the vertical line, these are behind, and any group that lies on the horizontal line, these are in front. So with this set, any groups that lie on these horizontal lines, these are going to be in front. So we're going to make always our hydrogen to be in front. It doesn't matter if you put your hydrogen to the left or you go ahead and you put your hydrogen to the right. It doesn't matter. So on 3, I have a hydrogen. I'm going to go ahead and put it to the left because no matter what position you choose for the hydrogen, left or right, you're going to get its mirror image anyways. And then I'm going to end up having my hydrogen on the CH3 on the other side. For 5, I'm going to put my hydrogen over here and I'm going to put my OH over there. Okay, so that is going to be the Fisher projection of this molecule. So again, your long carbon chain is along the vertical line. You label your chiral centers. So here I do have 2 chiral centers in there. In between, I have carbon number 4. This is not chiral. So as you can see, it's not necessary that the vertical and the horizontal line, when they meet, it's a chiral center. This one is a chiral center, this one is a chiral center, but this one is not a chiral center. Make sure when you transfer your molecule into a Fisher projection, you include every single carbon in there. Now, once this is going to be the first stereoisomer, I still have 3 more. So to get the second one, do the mirror image. So we're going to go ahead and do a mirror here, and then draw the mirror image of the molecule. Now, whenever you want to draw the mirror image of a Fisher projection, you keep the vertical line the same. You don't change it. So you have a CH2, CH3, and then a CH2 and a CH3 in there. And then you invert all the horizontal lines. So now the CH3, you're going to see its reflection on the side. You have a hydrogen here. Those two are not, this is not a chiral center. And then the OH, you're going to see its reflection on the other side. We're still going to have 2 chiral centers in there. Chiral centers are now going to increase. So whatever you start with, you're going to work with. So far, I have molecule A and molecule B. A and B are pair of enantiomers. These are mirror images of each other. So these are mirror images. Okay. Now to get, these are 2 stereoisomers out of the 4. To get the other 2, we're going to go ahead and fix 1 carbon from B. So this is the B Fisher projection. You have 2 chiral centers. You're going to fix just 1 chiral center. It doesn't matter if it's this chiral center or this chiral center. Just fix one. So we're going to fix this chiral center and rotate the other one. I'm going to fix the one at the top. So here you go. So fixing the one at the top will keep the CH3 to the left. I have my hydrogen and I have my CH2, CH3. So this one is fixed. And then I'm going to rotate the second chiral center. Rotation of the second chiral center is always along the horizontal line. So again, you keep the vertical line the same and you rotate 180 degrees every single time to go from one stereoisomer to the other. Don't rotate by any other angle other than the 180 degrees. So now this hydrogen will become here and this OH will become there. So I will have my hydrogen here and my OH there, and then I'm going to have my ethyl group in here. Now this one, we're going to go ahead and get its mirror image. This is a hydrogen, and an OH. Again, to get the mirror image of a Fisher projection, you leave the vertical line the same and you just rotate the horizontal line by 180 degree. The only rotation that is allowed with Fisher projection is 180 degrees. So here you go. And this is going to be the mirror image of this molecule here. I'm going to label those C and D. So this is C and this is D. So C and D are also a pair of enantiomers. So here I do have two pairs of enantiomers. I have A and B to be a pair of enantiomers, and then I have C and D to be a pair of enantiomers. Now let's go ahead and get the configuration for each one of them. For not to waste too much time in the configuration, if you get the configuration of just the first one for A, for molecule A, you can deduce it for the others. So here you go. You start with the chiral center, your first chiral center here. Let's go ahead and put the groups around the chiral center. So this chiral center is connected to a carbon, and a carbon. This is a tie. Then you move along, it's a carbon, oxygen, carbon, carbon, hydrogen. So definitely this group over here for carbon number 3, this whole thing is going to be 1. This is going to be group 2. This is going to be group 3, and that is going to be group 4. And the way that I am doing the rotation here, I'm doing it by 1. So I'm starting with 1 here. I'm going to 2, and then I'm passing by 3 like that. So for carbon number 3, the absolute configuration is going to be clockwise. It's an R, but take a look. Hydrogen is in front. Hydrogen is in front. It is not behind. The reason why it's in front, again, because when you are looking at the Fisher projection, any group that is located on the horizontal line is in front. And we cannot have, whenever you're doing the configuration, you cannot have hydrogen to be in front. Hydrogen needs always to be at the back. And it's not recommended to go ahead and put the hydrogen here along the vertical line. So the rule is keep it always on the horizontal line. Do the configuration, and whatever configuration you get, just go ahead and invert that. So this is an R inverted, and now it is going to be an S configuration. Okay, so that is going to be for 3. Now for 5, we're going to do the same thing. For 5, it's connected to an oxygen, so definitely this is going to be priority number 1 in there. This whole thing is going to be priority number 2, and that is going to be priority number 3. This whole thing is priority 2 because take a look at how many carbons it's connected to. So a carbon and a carbon. Here it's connected to a carbon and the hydrogen. So this is going to be a priority 2. That is going to be 3, and the hydrogen is going to be priority 4. And you're going by 1, 2, and 3 like that. And that is going to be counterclockwise. It's an S, but the hydrogen is in front. So that is going to be an R configuration. Now, the moment you see or you get your configurations for the first stereoisomer, you can deduce it for the second. So enantiomers, they have opposite configurations. So if this is an S, then this needs to be an R. And if this is an R on carbon number 5, then this is definitely an S configuration. This is the mirror image of the molecule. So the mirror image always have an opposite configuration because after all, these chiral centers are the stereocenters. So there is a rotation around the stereocenters and you are studying its rotation to the right and to the left. So once you're done from these pair of enantiomers, now let's go ahead and do the configuration for C. We fixed the first chiral center. So this is supposed to be an R. We didn't do anything to that in there. However, the second chiral center, we rotated that 180 degrees. So instead of S now, it's going to be an R, and its mirror image has to be the opposite. So it's going to be an SS. This is how you figure out the configurations. Now, with respect to the relationship, we said A and B are pair of enantiomers. These are mirror images. C and D are mirror images and they are pair of enantiomers. However, there is a difference between A and C, B and D, B and C, and A and D. And the difference is in the rotation of just one carbon. So if you look at B and C, you would see that the first carbon is fixed. It has the same chiral center. And then the second carbon or the second chiral center in there has different absolute configuration. So these, we're going to call them diastereoisomers. So diastereoisomers, these are isomers that are not mirror images. So here we have A and C, A and D, B and C, and B and D. All of those, they differ by one chiral center, not by two chiral centers. So by definition, enantiomers, they need to differ by two chiral centers in there. And to figure out your enantiomers every single time, you guys, always do the electronic configuration. That will be easy. So if you see that the chiral centers, they differ by all the carbons, this is enantiomers. And if you see that the chiral centers, they differ by some of the carbons only, these are diastereoisomers. So here, because I do have two chiral centers, if the compounds differ by one chiral center, then this is called a diastereoisomer. So these are called diastereoisomers. Diastereoisomers are not mirror images. These are different than enantiomers. Enantiomers are mirror images. They differ in all chiral centers. So let's have an example. If you are given two molecules and you are asked, go ahead and find the relationship between those two molecules. There's a lot of practice in the practice sheet. Please do that. But in order to solve these types of problems, the first thing that you do is you locate your chiral centers. So locate the chiral centers, and after you locate the chiral centers in there, you check the groups around the chiral center because there is a possibility that you end up getting a different molecule. So these will be completely different molecules in there. So make sure that the groups are the same. For example, here I do have a bromine and the hydrogen. I do have a bromine and the hydrogen. I don't care about the orientation of the bromine and the hydrogen, but I care about the connectivity of atoms. So make sure that the connectivity of atom is the same, because if the connectivity is not the same, then you are working with two different molecules now. Okay, so the relationship between them, there will be two different molecules. This carbon over here has an OH hydrogen, so same connectivity, a carboxylic acid, same connectivity in there. So these are stereoisomers. Now I need to figure out what type of stereoisomers are they. Are they enantiomers or are they diastereoisomers? Or they can be the same, identical. To do the configuration. So I need to do the configuration for each chiral center to determine. And if they differ by both chiral centers, then they're going to be enantiomers. If they differ by not all the chiral centers, then this is going to be diastereoisomer. Here I have two chiral centers, so they should differ by at least one chiral center to be diastereoisomer. And if the configuration is the same for both chiral centers, then these are going to be identical. So do your configuration in there. And on this carbon, okay, this is the carbon number. Okay, so on this carbon over here, I'm going to start numbering from my carboxylic acid. It's fine, you are not numbering to name, so you can number anywhere you want in there. But I started numbering from my carboxylic acid to give carbon number 2, do the configuration for that. And it's an S configuration, and carbon number 3 is an S configuration. Number exactly the same way so that to look and see what happened to carbon number 2. Did it change in configuration or stayed the same? So 2 stayed the same, but 3 changed. So these, they differ in one chiral center, then definitely they are diastereoisomers. Now, cis and trans is a form of a diastereoisomer. And we label them diastereoisomers if there is a chiral center, something like this. So if you have a cycle and you have a cis and a trans, those two now are going to be a diastereoisomer because they differ in one chiral center. So here they do differ in one chiral center in there. So we call them diastereoisomers. No. On the other hand, if we have an alkene, there is no chiral center in here. So these are called geometrical isomers. In chapter 4, we've learned how to change the cyclohexane into a puckered chair conformation and how to draw the groups on the cyclohexane using the puckered chair conformation. So here the groups, they need to remain in the same orientation pointing up, and this is the cis and this is the trans. So if I have these two, something like this, and I ask you what's the relationship between them, the first thing that you would need to do is figure out the orientation of these groups with respect to each other. So these are trans and these are on the same side and these are cis. So cis trans, immediately, because you have chiral centers, immediately that is going to be a diastereoisomer. Now, if you are given a cycle and you want to draw all its stereoisomers, you cannot use Fisher projection with cycles. Fisher projection is only used with a chain and not a cycle. So with cycles, you have to consider the cis and the trans, especially when you are working with a di-substituted cycle. So the first thing that you would need to do is locate your chiral centers. You have two chiral centers, calculate the number of stereoisomers. Whatever you get is the maximum number of stereoisomers in there. Then you have the possibility of these CH3s being either on the same side, which is going to be cis, or they are on opposite sides, which is going to be trans. Let's start with the trans in here. Having the CH3s being on opposite sides, locate your hydrogens, please. And then do the mirror image. Guys, the mirror image of trans is always a trans. The mirror image of cis is always cis. So pay attention to that. Because if you go from trans to cis, this is diastereoisomers. We want to keep the enantiomers here because A and B are enantiomers. So if you start with a trans, you need to end up with a trans. Do the electronic or the the absolute configuration in this case. And here I'm going to end up having an RR for both carbons, chiral centers. Then the mirror image is going to be the opposite, which is going to be an SS configuration. This is going to be the two stereoisomers out of the four. I still have two more. So now for the other two, I'm going to consider the cis isomer. Now, with respect to the cis isomer, now here's what comes another definition for an achiral compound. So at the beginning of the chapter, I mentioned that it's not necessary whenever you have a chiral center to have a mirror image. Sometimes you have a chiral center, but you don't have a mirror image because you are able to draw a plane of symmetry and the mirror image is within the molecule itself. And this is the case over here. So whenever you have a compound that you are able to draw a plane of symmetry across and cut the molecule in half, the first half is superimposable on the second half. Then in this case, this molecule does not have a mirror image because whatever you draw is going to be exactly the same as this molecule. Just rotate in there. And as you rotate 180 degrees, you are going to get exactly the same molecule. So the idea here is that if you have groups that are the same, notice here CH3, CH3, this carbon is similar to this carbon, is CH2, CH2, and the CH2, CH2. I can draw a plane of symmetry. So the moment you can draw a plane of symmetry, keep always this option in mind. Always try and see if you're able to draw a plane of symmetry, the molecule will not have a mirror image. The molecule will exist as a meso compound. You just show the molecule here. You don't show its mirror image, and you say that it exists as a meso compound. Meso is whenever you have 50% R, 50% S. So if you have your chiral centers in there, let's say two of them, one of them is going to be R, the other one is going to be S. Let's say if you have four chiral centers, then two of them is going to be R, two of them is going to be S. So the idea is that 50% of the chiral centers need to be in R, the other 50 is S, which makes sense because this acts like a mirror. So if it's a mirror, then you should see the opposite configuration of the second stereo center in there. So always meso has RS configuration 50-50. You're able to draw a plane of symmetry in there, and the groups around the chiral centers, they have to be the same so that the when you draw a plane of symmetry, you cut the molecule in half, these halves are superimposable on each other. And we would say that C exists as a meso compound. Meso compounds, these are, as we said, compounds that have chiral centers but they don't have mirror image. This is going to make them optically inactive, meaning that they are incapable of rotating the plane of polarized light. Even though they have chiral centers, you can draw a plane of symmetry, and the moment you can draw a plane of symmetry through the molecule, you will not have a mirror image in there. So that will make the molecule optically inactive. So the total number of stereoisomers for this example is going to be 3 and not 4, a pair of enantiomers and one meso compound. Let's have another example here. Now this is a chain, we can use a Fisher projection. So you want to draw all the stereoisomers of 2,3-dihydroxybutandioic acid. Whenever I give you something like this, since we did not cover yet the naming of the carboxylic acids, I'm going to go ahead and draw the structure for you. So locate your chiral centers, please. And these are two chiral centers here. And then draw your Fisher projections around these two chiral centers. So you have a carboxylic acid group here. This is your carboxylic acid group. Here, Okay, and you have another carboxylic acid group there. Remember what we said about the carbon chain, and the carbon chain needs to be on the vertical line. And then you have on carbon number two, so this is carbon one, carbon number two, this is the three, and that is four in there. Carbon number two has an OH and the hydrogen. Always put your hydrogens on the horizontal line and then invert your configuration in Fisher projection. And same thing for three, put your hydrogen on the horizontal line and invert your configuration. You can put your hydrogens anywhere. So I decided to put my hydrogen here, one on the left, on the right, the other one on the left. No matter where you put them, you're gonna do the rotation, so you're gonna end up getting the other possibilities, all the other possibilities. Calculate the number of stereoisomers, and this is the max that you can get. You can get less than that if you are able to draw a plane of symmetry. So you're going to start with this molecule in here, get its mirror image again to rotate. Fix the vertical line, always rotate both horizontal lines 180 degrees so that you can see the reflection. If you do the configuration, this is going to be S, this is going to be S. Its mirror image is going to be both R's in this case. And then we're going to fix one carbon, rotate the other. Here I am fixing the carbon in the first carbon in a chiral center, and I am rotating the bottom one. So fixing this one, rotating the bottom one. If you rotate the bottom one, you're going to end up having the hydrogen here and the OH there. The moment you see something like this, you are able to draw a plane of symmetry. The groups are the same. To be able to draw a plane of symmetry, the groups need to be the same. And you can easily see here that the groups are the same. All the groups are the same here. So here you go. Now you're able to draw a plane of symmetry. So no need for you to draw a mirror image, because whatever you draw is going to be the same as the structure. So we're going to say that C exists as a meso compound in there. And meso compound is made up of 50% R, 50% S. So this one was fixed on R, then definitely this guy is going to be S. So it's going to be 50% R, 50% S, which is going to make the molecule optically inactive. So this guy here is optically inactive. So by definition, meso compounds, these are compounds that have the same groups around the chiral center. So you're able to draw a plane of symmetry across the molecule, meaning that the molecule will not exist as a mirror image. The molecule will still have chiral centers. But because you're able to draw a plane of symmetry, the molecule will not have a mirror image. So the molecule will exist as a meso compound, and it will be optically inactive, meaning that it is not capable of rotating the plane of polarized light. The Another example is drawing all the stereoisomers of 3-methyl cyclohexanol. So the OH and the CH3 can either be trans or cis. Start with the trans, get its mirror image. Here I am showing you how to change it into a chair conformation. You guys keep the same orientation. So if the OH is up, keep it up. If the CH3 is down, keep it down. The OH and the CH3, they are located on carbons 1 and 3. So go ahead and label your carbons in there anywhere you want so that you have your groups on carbon 1 and carbon 3. Here, just to show you that the mirror image of a trans is always a trans in there. So this is up, down. This is up, down. So mirror image of trans is always trans. Mirror image of cis is always cis in there. And then you draw the cis isomer now. See? Now, not every cis isomer you can draw a plane of symmetry. For this one, you cannot, because the CH3 is different than the OH. Then, in this case, the cis will have a mirror image in there. And the mirror image of cis is always cis. So this also exists as a pair of enantiomers. And of course, if the molecule doesn't exist as pair of enantiomers, then they will be diastereoisomers. So BC, BD, AC, and AD, these are all diastereoisomers. Erythroendotreo shows the position of the functional group in the Fisher projection. So if the functional groups, they belong to the same side, then we call this erythro. And if functional groups, they do belong to opposite sides, something like this. So the bromine and the bromine here, they belong to the opposite sides, then we call this treo.